So, I hope everyone is doing well. We are going to continue our lecture today with where we left at on Tuesday. So, a couple of takeaways from our previous lectures regarding lattice theory and lattices. We've gone through various definitions of that we use to sort of build up to the point where we can define what a lattice is, which we're going to use to define the analysis domain to be able to compute the analysis results. And one of the main takeaways there is that a lattice is basically a partially ordered set that comes equipped with a binary join operator and a binary meet operator. We have also defined a complete lattice where we can define a least upper bound for every single element in the lattice and a greatest lower bound for every single element in the lattice. And if we cannot define such an element, we can't actually say that a complete we cannot label this lattice as being complete. The other thing, so basically a complete lattice is a lattice where you can define the meet and the join operators to any arbitrary subset of that lattice. However, if that's not possible, if you cannot define it for all possible subsets of the lattice, at least you can define what we call a bounded lattice, where you can define an element that has a higher order than all the other elements in the lattice, so that represents the upper bound of the lattice that we're talking about. In this case, it's D6, and we are going to call that element top, or T. And the bottom element of that lattice is the element that is basically the lowest boundary of the whole lattice. So it is bounding it from the lowest order of the lattice. And we're going to call that element bottom, or the inverted T symbol. Similar to defining join semi-lattice and meet semi-lattice, we can also define bounded join semi-lattice and bounded meet semi-lattices. And then we ended up with a couple of questions for that segment of the lecture regarding whether a complete lattice is bounded or not, and whether a finite lattice is complete or not. I think we have gone through the first question during the class, but the second question, I encourage you to think about it at home and come with questions about that. Come with any questions you have or any thoughts or ideas that you have about this question here. So I'll just pause for a minute here in case you have any questions, or you want to share any insights or any answers or any comments or concerns about the second question on this slide here. By the way, I would strongly encourage you from there on, because I can't keep my eye on the text chat all the time during the lecture. Otherwise, I would just be looking elsewhere instead of like on the screen. It will just look weird and I will be distracted. If you have a comment or a question, just enable your voice for a few seconds there to voice out your concern or question or comment, so that I can just get to it right away. So just interrupt me while I'm speaking. Don't wait for me until I'm done with the current part that I'm talking about. It will just be less distracting for me than waiting and then looking at the message chat. So I'll only look at the text chat every time that I have an explicit pause during the lecture, so that I reduce the number of distractions that we have throughout the lecture. So I take it then that there are no comments or questions about this part so far of the lecture that we have in the last week. On Tuesday, 2 days ago. Then we've gone through a few more questions regarding lattice theory. We talked about a lattice of finite and cofinite elements from natural numbers, and we had a few questions whether this would be a lattice or not, whether it's bounded or not, whether it's complete or not. Again, we have gone through the first two questions here in class. And I also encourage you to work out the third question at home. So again, I will pause here for a few seconds in case you have any questions about the third part or the third question on this slide, or any comments that you would like to share. What is the song that you're playing before each lecture starts? So I think I actually have it there in the credits for on the same slide before the lecture, but I'll I'll pick it up. I'll look it up. Sorry, from the recordings. But you can see, like, if you check out any of the previous recordings, you will see it. You will see the link to it right there. You're welcome. Any other comments or questions about other things than the song I play at the beginning of the lecture? Haven't worked on my playlist for the break in the middle of the class though, so if you have any ideas, just send them my way, please. So after that, we have also gone through a couple more definitions that will help us define further properties of lattices. So we talked about the lattice chain that basically gives you an idea about how you can find or compute the height of a lattice, or the size or the length of a lattice, which is basically the size of the longest chain or sequence of elements in that lattice. Then we talked about the ascending chain condition, which basically guards or governs the way that you can talk about or you can define a lattice that may have infinite number of elements in there, but still would be considered a lattice because it satisfies all the other properties. It might not be a complete lattice, but it's probably, if you can define a top and a bottom element, then it would be a bounded lattice in this case. And we also said that lattices may be infinite as long as they can satisfy that ascending chain condition, which basically says that you eventually stabilize any sequence that you are, any infinite sequence that you may have in the lattice, or any infinite chain that you may have in the lattice. And what do we mean by stabilize? Meaning that you eventually will converge to a single element that potentially could go all the way up to be the top element in your lattice. Otherwise, this will violate the antisymmetry relationship, or the antisymmetry property of the binary relationship that governs the ordering, or that orders the elements within that lattice there. And I think after that we had a couple of takeaway messages about lattices. We had a few types of lattices that we discussed also at the end of the lecture, like power set lattice, product lattice, and map lattice. And then we finally, during the last couple of minutes of the lecture, we started using lattices in a sort of a more meaningful way. And the example that we have gone through in the lecture was showing side by side what would happen if, on a control flow graph, the CFG of a piece of code that contains a loop, for example, which we have discussed in maybe 2 lectures or 3 lectures ago, what would happen if we're using a lattice on the left-hand side versus what would happen if you're just using sets on the right-hand side there. And eventually, we found that the lattice would eventually enable us to define an infinite number of iterations in this loop, because you can always just go to the safe over approximation, or the element that has a higher order in this lattice here, which is a lattice of natural numbers, because we are talking about ranges of integer values that can be computed over, or that the loop is computing on. And these were some few lattice hacks that would be useful if you're thinking about defining your own lattice or defining your own analysis domain. And that was the end of the previous lecture on Tuesday. I'll again pause here for a minute and ask if anyone has any questions so far, any comments, any concerns, anything that you would like to bring up before we move on to the next segment of this lecture. All right then. So now that we have defined the second major component that took us basically almost 2 lectures to define, which is lattices, that will define the analysis domain. And prior to that, we also discussed about the direction of the analysis, whether it's going forward or whether it's going backward, and that will determine the direction that the analysis will scan, basically the control flow graph or the intermediate representation that you choose for your analysis. Now we're going to define the third major component that would enable us to transfer information or data from one statement to the other, and how each statement may affect that data that is being transferred, which is flow functions. So the first thing, if you remember from the name of the framework that we're just talking about for the last 3 lectures or so, it's called the monotone framework or the monotonic framework. So what does that mean? What does monotonicity here means? So monotonicity means the following. So if you have a poset U with a binary ordering relationship, and this poset is a lattice, then the function f, whatever function you have, f, is monotone, meaning that it will preserve the ordering if the following criteria is true, or if the following condition is true. If you pick any 2 elements, x and y, from the set U that defines your universe or your domain, then you find that y has a higher order than x, that basically what the left-hand side of this implication means, then the result of applying the function f on y must have a higher order according to the same binary relation than applying the function on x. So pick any 2 elements here. If one element has a higher order than another, b is higher than a, 2 is higher than 1, if you apply your function f, which is, let's say, multiply natural numbers by 2, then 2 is higher order than 1, then 4 must be larger than 1, or has a higher order than 2, right? So if that's the case, then this is a monotonic function. Then f, the function here, which is multiplying by 2, would be a monotonic function. So let's pick some elements here from this lattice that we have in front of us. So I'm going to pick d5 to be my x. And f of x, let's say that I define the function f such that f of x would yield d1 in this case. So this is d1 is going to be my f of x. Now if I pick y to be d3, and my function f would yield the value d2 to be f of y, then d2 has a higher order than d1 in this case. So so y has a higher order. So y here has a higher order than x, d3 has a higher order than d5. Applying the function on y yields d2, applying the function on x yields d1. d2 also has a higher order than d1, so everything is good to go. So we're good to go here. This would be a monotonic function. So what if my function f yields d0 as my f of y? Again, we're good to go, because f of y here, d0, would have a higher order than d1, using the transitivity property of that binary relationship, right? So that would mean that f of y would still have a higher order than f of x. So again, this is a monotonic function. So what happens if my function f, when I define it, my flow function f, would yield the value d6 to be f of y? So if the function f is applied to d3, the value is d6. What do you think happens in this case? Would this still be a monotonic function or not? Okay, so it's not a monotone function in this case. And why is that? So it seems that my speakers are not connected. My headphones are not connected, so I didn't hear what you said, Jackie. There we go. Now I can hear you. There is no relation between f of x and f of y. Right. So in this case here, f of y, and strictly the relation that we are looking for is that f of y needs to have a higher order, must have a higher order than f of x. And that is not the case here, so that would mean that this is not going to be a monotonic function if we define the function f that would yield f of y to be as such. So in other words, what does a monotonic function mean in this case here? It means that you are getting a less precise input, but that does not result in a more precise output. Because remember, like if we're defining our lattice as such, going up in the lattice, having a higher order in the lattice, means that you are getting a less precise, a safe over approximation, right? The higher you go in the lattice, the more over approximation you are reaching. The lower you go in the lattice, the more precise result you're reaching. So if I'm getting a less precise input, logic says that I should not get a more precise output out of it. And if that's the case, that is not a monotonic function. And we're going to see later today in the lecture and also in the next lectures why this monotonicity property is important to guarantee to provide certain guarantees on the analysis itself. So in this case here, this is not going to be a monotonic function, and we are not going to it's not going to be a monotonic function, and we cannot depend on that property for this function here, f. So far so good. Any questions about monotonicity here for flow functions? All right, so now that we have defined what the analysis domain is in terms of lattices, and we have defined what the direction of the analysis might be and how that might affect how we scan the code, and we have defined what flow functions are, now we need to put everything together to define our analysis and our algorithm to see how the monotone framework would handle that. So the first thing that I would like to talk about is the lattice fixed point theorem by Alfred Tarski from 1955 that basically says that use the property that if you have a complete lattice, then you would also be able to define a lattice of solution, and you would be able to define an algorithm that would eventually terminate if you compute over that lattice. And that is one of the main reasons why we need for a program analysis, or for program analysis to be able to define a lattice, ideally a complete lattice even, so that we can converge to our result faster and guarantee that our analysis actually would terminate. So this is what guarantees that our analysis that guarantees that our if you have a complete lattice story, that you're going to get the most precise analysis result out of it. And that was developed by Alfred Tarski back in 1955. So now that we know that, what does the monotone framework do with all those definitions and with lattice theory? How do we define our algorithm to solve a given analysis problem? So we're going to scan the control flow graph, and for every single statement S in the control flow graph, we're going to define the following. So we're going to define a flow function. So remember, the flow function will be defined for every single statement, and it will be given an input lattice. It will map it to an output lattice. So this is a map lattice here. You're given an input lattice, and you apply the flow function to its elements, change some values in there according to the flow function, and you get an output lattice on the other end. And then you have many of those along the way, because you have given a path in the program, you have multiple statements denoted by statement number 0. So this is the very first statement or the entry point of the program. Statement number 1 is the next one, statement number 2, all the way up to the current statement that you're interested in, which is Sn, or statement n, through the control flow graph. And we're going to define the flow function of that path to be the composition of all the flow functions along the way, given the input x. Remember when we did that 2 or 3 lectures ago, when we had 2 paths in the program, where one path was the true branch, one path was the else branch, or the false branch of an if statement, and we had the function composition of all the functions or the data flow functions along one path to define this path, and we had a similar function composition but for the false branch, and then the join of both paths was the summary or the abstraction of the whole program. We're going to do pretty much the same thing here. And the goal of our algorithm is that we want to find the join of, or the meet over all paths solution, the MOP solution, which in our case here is going to be the join over all paths solution, because you want to join all the all the different paths in the program to find the over approximation of the whole behavior, the runtime behavior of your program. So we want to find the MOP solution, which is the join over all paths, which each one of them would represent the function composition of the flow functions along that path. So this is what we want to compute. Generally speaking, again, it is not going to be computable, just like everything else in program analysis. Again, referring to that 1977 paper by Kam and Ullman, this MOP is generally uncomputable. So now we're going to define certain workarounds that would enable us to compute a safe over approximation for this. And by safe here, I mean sound. In other words, a solution that does not ignore any potential runtime behavior of the program. It might include some false positives, admittedly, but it won't ignore any potential runtime behavior of that program. So how are we going to do that? So we're still going to have the same control flow graph. We have the same statements in the program. We're still going to define a function fs on the map lattice L to L with a subtle difference. So now we're going to define some intermediary values here. And those intermediary values are going to be the following. We're going to have a vs in and a vs out. Vs in is going to be the input values to the function, or the arguments to those flow functions, and vs out is going to be the output or the result of applying that function to the input. Both elements are going to be, or both values are going to be elements in the lattice. And what we're going to do is that for the input to every flow function will basically be the join of all the v-outs from the previous paths up to that point so far. So at any given statement, you will figure out what is the v-out of all the paths coming into that point, find the join of those values from the lattice that we have defined. This is going to be the vn or the vsn to that function, and then this is how the data is going to be propagated from one statement to the other. So this is a subtle difference compared to here, where you just apply the function composition all the way from the very initial point of the program up to that point in the program, and then you find the join over all paths. Here, in this case here, we're going to have some intermediary steps along the way. And we'll see that will enable us to have a computable solution at the end. And we are going to try to make it as precise as possible compared to the actual solution that we would have ideally computed. This solution here that we're aiming to compute is called the least fixed point solution, or the LFP solution, the least fixed point solution, which is the solution that has the highest precision. And this is what we're going to be aiming for. There is another solution. So this solution, according to the Tarski's theorem and the monotone framework, is going to be guaranteed to have to have at least the same precision as the join over all paths solution, the MOP solution, meaning it is going to be a safe over approximation, right? So it is going to guarantee that it will be a safe over approximation of the meet over all paths. Sorry, my headphone is giving me a hard time today. Can you folks still hear me well? Just indicate on the Zoom chat if you can. Oh. Lost my audio. Your audio is cut out. Twitch is fine. Zoom is not. All right. Can you still hear me on Zoom right now? No? Yes, I'm back. Great. Sorry about that. I don't know what's happening with the audio connection today. It's giving me a hard time. Sorry about that. All right. So we want to compute the least fixed point solution, and the main thing about the monotone framework is that if we define it as such, it will be a strict over approximation. It will be a safe over approximation of the MOP solution, which is ideally what we would like to compute, but it is not computable in the general case. Okay, so this is good enough. It's going to be a good over approximation, and we're fine with that, and we can just move on with our lives and see what else we can do with the analysis results. So having defined all that, this is actually going to be the algorithm that is configurable enough that is going to solve various classes and different classes of static analysis using the monotone framework. So this is the general data flow algorithm. First, we're going to initialize. Remember, you need to initialize the outsets of all the statements to be and the input statements to be the bottom value. So you're starting with an initial value that says, I have no idea what those values are going to be, so I'm just going to say, I don't know about anything. I don't know what the value could be. So you're choosing the bottom value of the lattice. You don't know anything about it for all statements. Then it is going to be a work list algorithm, meaning that the algorithm is going to keep running until the work list is empty. So the first thing we should do, we're going to add all the statements to the work list. And then we're going to pick one statement, whatever statement, just pick one statement from the work list. Let's say it's going to be S. This is statement number 4. And we're going to define, to find all the predecessors of the statement S, right? And we are going to find out the join of all those predecessors of S. And we're going to add that or concatenate that with the out of the current point P in the program. And then we are going to assign that to be the input to the current statement. So at any given statement, I'm going to figure out what are the all possible paths, or excuse me, what are all the predecessors of my statement S, find out their output statement, their outsets, and find the join of all those outsets. Make that be the inset of the current statement. And now what will be the outset of the current statement, meaning what will be the result of the data flow function when it's applied at the current statement? Well, it will be exactly that. I will apply the data flow function fs to the current ins s. So these two statements here are the ones that are vs_in and vs_out in the previous slide. So basically line number 5 here, I'm finding out what all the vs_outs of my predecessors, finding the join of all of them. And in line number 6 here, I'm using that join to be the input to my current flow function, apply the flow function, and then the next is the point that would enable me to continue further in the analysis and terminate eventually. So that point in number 7, that condition here, checks whether the outset of S has changed or not based on my computation. because if it has changed, then that means I need to update all the other statements that may depend on the current statement that has changed, right? So if that's the case, I'm going to add all the successors of S to the work list because I need to compute over them again. If not, then there is no need to compute over them again, and then I'm not going to add all those successors. Otherwise, I'll just keep going to the next element on the work list, pick any element you want, do the same operation again, and do this over and over and over and over and over until the analysis eventually doesn't have any elements, any more statements in the work list. And once that's the case, then the analysis will terminate, and all the values in the outsets of all the statements are going to be the result of the analysis at that statement. So if you want to know, for example, at that point, what is the constant value that a variable x may hold at the end of the function, because we are still talking about an intra-procedural analysis within the boundaries of the same function, it will be the out s, or the outset of the last statement of that function. So if you check out the last statement of that function, that will give you the value that you're looking for. And that would be the generic data flow algorithm for the monotone framework. Any questions so far? I'll again pause here for a minute or so if you have any questions or comments. All right. So the second theorem that I will briefly mention in today's lecture is a clean fixed point theorem. And this is the theorem that guarantees termination for bounded lattices. So this is related to having the ascending chain condition, right? And this is why precisely we need to have a monotone flow function. So the fact that we can define monotone, that we must define monotone flow functions in this monotone framework enables that it will comply to the ascending chain condition, which means that our lattice will be bounded, even though it may not be complete, because it might not have necessarily at least upper bound and agreed lower bound for all possible subsets. And all those properties together will guarantee the termination of our analysis, meaning that even though, generally speaking, static analysis should not terminate because you are reasoning again about the behavior of the program without running it, and to reason about the behavior of the program, you need to run all possible execution paths of the program, which again boils down to Rice's theorem, so your analysis should not terminate. But having this monotone flow function, this property of monotonicity, will eventually guarantee the termination for bounded lattices. So it is not enough to define just a lattice for your analysis domain. You need to make sure that if you want your analysis to terminate, it should be a bounded lattice. If you want your analysis to compute the most precise result, it should be a complete lattice. And these two properties are guaranteed by the clean fixed point theorem and Tarski's fixed point theorem, respectively, or the lattice fixed point theorem by Tarski, respectively. So what's all that talk about the meet over all path, or the join over all path, sorry, and the least fixed point solution, and so on and so forth? Well, what's the deal with all these solutions? So assuming that this is the universe of all solutions that you may have, right? So if this is the universe of all the solutions that you may have, anything in that green region is a safe over approximation, so it is a sound over approximation, guaranteeing that you're not going to ignore any potential runtime behavior of the program. Anything in that red region means that it is not a safe over approximation or an incomplete solution, because it might actually ignore some of the runtime behavior of the program. So if this is our universe, assume that we're going to have a lattice of all the possible solutions or algorithms that the results that we may compute, right? So we can actually create a lattice of all those solutions. So top means anything can happen. This is the least precise solution that you may have, which is basically, yes, maybe. Remember when we discussed this in three lectures ago, I think, that we want to reduce all those maybe answers, the maybes in the answers to the analysis results? This is basically what a maybe is. Maybe says, yes, it could be, I don't know, right? We want to reduce all those, even though it is a safe over approximation. And we have a bottom result, which is basically, I don't know, nothing, I have no information, which is an unsafe over approximation. And in between, we have a whole range of results that we may compute. So the actual result that we want to compute is basically that result here, at this point here, right? This is the result that we want to compute, really at that tip between the two universes of safe and unsafe solutions. So the meet over all path, the MOP, or the join over all path in our case, is the solution that is still in that green range of solutions. It is still a safe over approximation, but has a higher order than the actual solution, meaning it's a safe over approximation. It is not exactly that over approximation, because we cannot get that actual solution actually, because of the fact that static analysis would reduce basically to Rice's theorem. So we have to find that this is the MOP is the best thing that we can aim for, the best thing that we can compute. However, generally speaking, it is not computable. So we're going to come up with workarounds that would enable us to compute it somehow. So the next best thing is the least fixed point solution, which follows from Tarski's theorem. And if you have that, then this is a good over approximation or a safe over approximation of the MOP solution. Then you can have the greatest fixed point solution, which is something that is of a less precision than the LFP or the least fixed point solution, but still a safe over approximation, and with many variations of configurations of analysis precisions, as we are going to discuss over the next 2 or 3 lectures. We're going to see various other analysis configurations that affect the precision of the analysis. You can have a wide range of fixed solutions that are all valid solutions, all safe solutions, but they vary in the level of precision between them. And it's really up to the analysis engineer and whomever is going to use the analysis results to determine what is the best thing for themselves. Do you want something of that precision, or a higher precision, or a lower precision? I'll just give you an example. If you are a security engineer at a company or something, you don't want your, if you are a security engineer, like as in somebody who would just scan basically the code for any potential vulnerabilities. Maybe you just don't want to miss any potential security vulnerability that your application or the code that you're scanning might exhibit before you deploy. So you want to have the maximum precision, and you're willing to sacrifice some false positives because of that. So you're willing to have some false positives in your code because of that. On the other hand, if you are the developer who is building that system, you just want to work on your solution, you just want to work on your development tasks, you just want to go through whatever bug reports you're getting, you're already overwhelmed with work, so you're not too concerned about having the most safe over approximation of the analysis results telling you every single security vulnerability in the code. So you don't want that, and you want actually as few false positives as possible, because more false positives in your case would just mean less time for you to work, to do the actual work that you're supposed to do, and it will just disrupt your workflow. So you're opting for a less precise solution, even if it's unsound or incomplete, for the sake of just moving forward with your daily life and daily development tasks. So again, every kind of precision, every kind of configuration has its own users and its own customers. So nothing says that this is the right thing or this is the wrong thing. It just depends on the context that you want to use this analysis for. So we have actual solution, MOP, LFP, GFP, and the top solution, and various fixed point solutions between the GFP and the LFP. Now, every solution, let's say S, has to have a higher order than the actual solution. And if it does, then this is going to be called a safe over approximation or a sound solution. The join over all path over the MOP always has a higher order than the actual solution. And the LFP, the least fixed point solution, always have a higher order than the MOP in the lattice of solutions. A flow function is called distributive if and only if the following condition is true. So if basically the result of f of x join f of y is the same as applying f to the join of x and y. Basically meaning if you have two elements x and y in your lattice, you apply the function on each element separately, then you do the join, you're going to get the same result as if in the case of applying the join first and then applying the function. So it doesn't matter what is the order of applying the join versus applying the function. You can do them interchangeably and you're going to still get the same result. If that's the case, then a flow function is distributive. If you're actually able to define all the flow functions in your program to be, in your analysis, to be distributive, then we have this nice property that actually the MOP becomes computable because it's going to be exactly the LFP. The least fixed point solution that you're going to compute is indeed going to be the join over all path solution. So this is the best solution that you can compute. And we're going to discuss this in further detail when we talk about the IFDS framework, another theoretical framework that is used actually quite widely in static analysis in practice to define distributive data flow analyses. One other thing that I'd like to talk about regarding the monotone framework is in the data flow, as the generic data flow analysis algorithm that I just discussed, we basically initialized all the values with bottom, right? You could have initialized them with anything else. You could have initialized them with top. So if you initialize them with top, that basically means you're basically going to go to the direction, to that direction, towards the MOP. You're always trying to go towards the MOP. So if you go towards the MOP, that means the first solution that you're going to find is just going to be a safe over approximation and the analysis will terminate. And that's not what you want. You want to get a more precise solution, which means you want to go further down in that hierarchy of solutions. You want ideally to get to the MOP solution if you have distributive flow functions, or the LFP solution if you don't have distributive flow functions. So that's why we actually initialize ideally the values with bottom so that we can go up in the hierarchy until we get the most precise over approximation. So if you start from top, if you initialize your values with top, you're just going to terminate early on, and terminating early means getting a lower precise solution, or a solution with lower precision. So this is actually all what I had to say about monotone framework, lattice theory, flow functions, the generic data flow analysis, the join over all paths, the least fixed point solution, very briefly about distributivity before we go into further detail later in the course, and some insight about the initialization of the analysis, MOP versus LFP. I'll pause here for a few minutes and we'll continue at 1:20 p.m. Edmonton time. If you have any questions, just you can write them in the chat. This would be a time I can actually read the chat, or you can just use the voice on the Zoom meeting so that you can voice your comments or concerns. We'll continue in a minute from now. Sorry, in 5 minutes from now. Yes, Oh, I don't think I heard you, Akalanka. Sorry. Have you posted your slides? I couldn't. Yes, I did post them. I just forgot to make the link visible on eClass. So I'll make that visible right away. Seems I'm still having some trouble with my headphones, Akalanka. So I can't hear you well, unfortunately. Don't know what's going on today.
Is it okay now?
Can you still hear me now, everyone? Okay. Yeah, I can't hear Akalanka speaking. Yeah, not sure why. I think my headphones. No, they are charged. I thought they might have run out of battery, but they are charged. Sorry, Akalanka, can you just maybe type out your question? That'll probably be easiest because I can't figure out why my headphones are not working. It's Thanks. No, it's not mute. It is on almost maximum volume, but I don't know why my headphone is not picking up. I don't know why Zoom is not picking up my headphones. It's picking up my mic just fine. Let's see. Yes, Robert, I did try to reselect the right speaker in my Zoom settings multiple times, but it's just, it sees that it is connected to my headphones, it's just my headphones are not picking up the sound. Okay, so back to Akalanka's question. This is about the sample lattice you drew to introduce a complete lattice. Can you maybe point me to which slide was that? When I talked about a complete lattice. Okay, so this is the slide that you're talking about, Akalanka, right? Slide number 84 in this topic. Okay. Okay, going back to your question, if we take a subset, say D1, D2, D3, D4, and D6. Okay, so this is your subset, D1, D2, D3, D4, and D6. It is not a lattice. Well, the definition of a complete lattice is not that every subset should be a lattice on its own, right? It just means that you can find a least upper bound for that subset and a greatest lower bound for that subset, right? So these are the definitions of what a complete lattice is. So it doesn't matter if your subset is not a lattice, it just matters that you can find a greatest lower bound for that subset and a least upper bound for that subset. So in this case here, what would be the least upper bound for that subset? It would be D6. This would be the least upper bound for the subset. Oh, you mean the greatest lower bound. Right. Let's go to the definition again. So the definition says if you have a poset where U is not empty, then this is a complete lattice if for all subsets A of U there exists some element Z in U, right, where Z is the greatest lower. Okay, so see, that's the point. You just need to get that element from U. So it doesn't have to be an element from A itself. So in other words, in this case here, the greatest lower bound for these elements would be the element D7, which is an element of U, but it doesn't have to be an element of the set of the subset A. So that was the main difference. So I think the confusion might have been that the greatest lower bound and the least upper bound must be in the subset, but it is not. They must be in the set itself, the universe, the whole universe. Okay, cool. So that resolves your question. Any other questions or comments about anything about the topic of lattice theory so far? Of course, if you have any further questions after you maybe rewatch the recording afterwards, or you start solving the assignment or working on the assignment, just shoot us an email right away, or post it on the eClass forum. Don't wait until right before the assignment deadline. All right, so if there are no further questions here, I think in the remaining time, maybe in the next 20-25 minutes, I'll start introducing our next topic of the course. Yes, exactly. This will clear up a lot of future confusion. So I'm going to introduce our next topic in the course, where we were going to get to see an application of all that theory that we have been defining and all those lattices and all that flow functions, and how different configurations of analyses may affect the precision of the result that the analysis may produce or may yield or compute at the end. And the first analysis, or the first type of analysis that we're going to go through, is called call graph construction. We're going to define what a call graph is, how we can build a call graph, and what we could use it for, and how the different analysis variations of call graph analyses may affect the precision of other analyses that may use that call graph as an input. Usually, this topic I started on a different lecture than the lattice theory lecture. So that's why there is this overview, but we just have gone through that. So again, a quick summary so that refreshing your minds from before the break. For all the solutions that we have the join over all path, we have the least fixed point, we have the greatest fixed point, we have a top solution, bottom solution, various other fixed solutions. Anything in the green zone is a safe solution or a sound solution. Join over all path is is safe compared to actual. LFP is safe compared to the MOP. If you have if all your functions are distributive, if your function is distributive, then it doesn't matter. You apply the function first or you apply the join operator first. Both will yield the same result. If all the functions are distributive, then the LFP is the same as the MOP. If you initialize with top, you terminate early, you get a lower precise or an analysis with a lower precision. So just to remind you again, when we design a data flow analysis, you need to configure 5 parameters. The analysis direction, forwards or backwards, depending on where the information you're computing or you are interested in is going to be available at, whether it's something about a future point in the program or something about that has already happened previously in the program. The domain of the analysis, so the lattice theory, the lattice that we're going to define. And that lattice, after we define the lattice, we need to define the flow functions, so the effect of the statements on the elements of this lattice, the values that the program will hold at entry points, and these would be drawn from the lattice elements that we have defined. And what is the initial estimate or the unique element that you may have to initialize the estimate that the analysis will compute. Could be top, it could be bottom, could be something else. How do you merge information? So the join operator, and we'll see how that will come in play later on in the course, and so on and so forth. So in that segment of the lecture, we're going to talk about call graph construction as one of the major analyses that is used in various different analysis frameworks. So here's a few examples of analysis frameworks that do have call graph construction embedded into them as their analysis suite. So this is LVM, Julia, Soot, one of the major analysis frameworks that started out of as a research project at McGill University in 1999 or so, has been used quite a lot both in academia and in industry since then. Findbugs, the Checker framework, Opal, and so on and so forth. There's also Dupe, an analysis framework by Yanis Margakis and others at the University of Athens, used quite extensively, again, both in academia and industry. It's based on data log, so it's logic rules that operate over analysis facts and compute further facts. Voila, which has been developed by IBM Research and is used in various IBM products and also used in research groups. Flowdroid, Coverity, and other security-related analysis tools. All these tools need a call graph to be able to cross method boundaries. So far in the course, we have only talked about analyses that reason about internal method bodies. So whatever happens within a single method, but doesn't cross the method boundaries to others. So the initial step to be able to do so is to compute a call graph that will tell you, if you have a method call, where do you go to? which method would this resolve to at runtime. So that's what a call graph would do for you. So what is really a call graph and how does it look like? What kind of data structure does it look like? So if you have seen any kind of code like this before, this is a code from a Java-like language, could be Scala as well, where you have a shape class, you have a circle class, you have a square class, and here you have a method called s.draw. And if you have your class hierarchy defined as follows, so circle and square, both classes extend shape or inherit from shape, basically a call graph will tell you whether this s.draw will go to circle.draw or go to square.draw. So this kind of analysis would be required by every single inter-procedural analysis out there. So now we are going from intra-procedural analysis within method boundaries to inter-procedural analysis crossing method boundaries. So far so good? I think I can hear you now, Akalanka. Great, yes, my headphones work again. I hope it did a few minutes ago when you wanted to ask your question. But it works now, good. All right, back to call graphs. So, now that we know what a call graph is, now let's start building a call graph for this program here. So if you look at this program, it's a very simple Java program that has a main method, and that main method, it has a main class, that main class has a main method, it has a whole bunch of statements in there. Based on some arguments that are passed to that main function, it is going to create either a circle or a square, and then it will call s.draw on that function, on that object. So if we're going to create that method, if we're going to create that call graph, we're going to go through that program statement by statement, figuring out what is possibly the method that could be called at that point. And I would like some help from you in the following minutes to build up this call graph as we go. So I'm going to help you out with the very first node in the call graph, which is the main method, main.main, because we are a public static void main, so we have to start from the entry point of the program. That's the initial method that we're going to call, right? So after that, I gave it away. So after that, what would be the first method that would be called if we move on to the next statement? So shape.s, would anything be called at that point? Yes or no? Can I repeat again? So what I would like you to help me out with is going through that program statement by statement. I would like you to tell me what would be the method that would be called next from the methods that we have up here. So I gave you the first method that we should call in the program, which is the main entry point or the main method. Now my next question is, what could possibly be the next method that could be called? So the next statement that we have in the main method is the declaration shape s. Would that call any method? No, right? Why? Because it's just a declaration method. It doesn't create any object, doesn't call any other virtual method. There is no method dispatch that would happen. However, in the next statement, which is the if statement, and remember, we're doing static analysis, we have to over-approximate the runtime behavior of the program, so we'll take both the if statement and the else statement. Very similar to what we did in the control flow graph. Remember in the control flow graph in the very first lecture that we had, we said that it is going to be an over-approximation of the actual control flow of the program at runtime, meaning that there might be some infeasible paths that are there in the control flow graph just because we cannot possibly have exactly what the actual runtime behavior of the program is. This is exactly the same situation here. We don't know for sure what exactly is going to be the method that is called at runtime, but our call graph has to be capable of representing all those scenarios. So there might be over approximation, there might be imprecision, but that's fine because we're willing to tolerate that just to be able to perform static analysis in the first place. So the first thing that we can call here is the constructor of circle. So circle.init. So this is going to be the first method that could be called from main. args.length, this is Java. Length is just a property of the array. It's not a method that will be called, so there is no method calls there. Now, what will be the next method that may be called from the main method? If you look at the else branch, what will be the method that may be called there? Right, it is going to be the square constructor. Because there, but actually, before that, in Java, and not just in Java, in many other languages, but the prime example is Java, when you call a constructor of a class, you just don't stop there. You just keep calling the constructors of all the superclasses all the way until you hit the top of the class hierarchy. So in Java, that means the following. If you create a class of object, of type circle, then you need to figure out what is the superclass of circle. It is shape. So I'm going to call the constructor of shape. What is the superclass of shape? It is the javalang object class. So I'm going to call the constructor javalang object. So just because you called this method here, you triggered all those method sequence calls here. So one method call in your main function triggered 3 method calls in the call graph, and they all have to be there in the call graph. Otherwise, your call graph is incomplete. That's just from the if statement. From the else statement, we can call the square constructor again, and the square constructor is going to call shape constructor, and that shape constructor is going to call javalang object constructor. And then at the main method, because we have either a circle object or a square object, that s.draw would be circle.draw or square.draw. So if you look at that call graph here, that will be an over approximation of the call graph for that main method for any potential execution of that program. So if you look at this call graph, pick any potential execution of the program, and you'll see the sequence of method calls there represented properly. What is the problem that you see with this kind of representation here? Do you see any problem at all? The sequence is missing. I'm not sure what you mean by that, Mohammed. What do you mean by the sequence is missing? What kind of sequence?
Can you hear me?
Yes, I can hear pretty well.
So what I said, like,
All right. Yes. Okay. So I'm not sure if. Right. So one issue with that is indeed that I don't know whether this circle constructor is called first before square constructor, or whether any of them would be called at all. Right. But I mean, one solution to that you can say is, well, we can just add labels to those edges and then say number them. Right. Just number those edges and then say for each node, see the edges, the outgoing edges from it, and just number them, give them a sequence. So that may resolve this problem. But do you foresee other problems there? What do you think could be another problem with this kind of representation? Right. Right, exactly. That's yet another problem with this is if I call, I'm giving away a lot of answers here just because of skipping through my slides on my iPad. But anyways, so that's correct. So if I call circle.init, I don't have anything that tells me that if you call circle.init, you should also be calling circle.draw. You cannot call square.draw because you have an object of type circle. So you cannot call square.draw. But again, we can sort of come up with certain annotations or maybe another data structure that can sort of administer these kind of relationships. But the problem is really related to all these problems together, right? Because what if we have another shape, let's say triangle? So what would happen for triangle to be one of those, if it's added to this program, then we're going to have triangle.init, right? And this triangle.init is going to call shape, and here we might have triangle.draw. And if you have one more shape, then you're going to add one more draw method and one more constructor to that. So the main problem with these kind of things is polymorphism. So if you're talking about an object-oriented language, whatever it is, polymorphism is going to be your enemy. It's going to blow up this call graph. It's going to exponentially increase the number of edges and nodes in this call graph. Just adding one class, as we have seen, you would add at least 2 edges and 2 nodes to the call graph. So let's take a few steps back to understand what exactly does that call graph represent, and how we can come around or find a workaround for this polymorphism, the problem of polymorphism, and how it may affect the precision and the correctness or the soundness of the call graph that we are computing. So let's say that our universe is going to be all the nodes that represent our program. So all those nodes, white dots that you see on this screen here, are going to be the methods that are in your program. So what does the call graph really represent? The call graph represents the calling relationships between these nodes. Which method call which other method? So what are we after? Ideally, we would like to compute a call graph that is basically the union of all the possible method call sequences that may happen at runtime. But again, just like everything else with static analysis, we cannot compute this ideal call graph because it reduces the Rice's theorem. So we cannot compute this ideal call graph, so we find over approximations, or we find approximations, not necessarily over approximations, it may be under approximations too. So this reduces to the halting problem, the ideal call graph, so we're not going to be able to compute it. So we revert to, or usually researchers or analysis engineers, static analysis engineers, would resort to over-approximating or finding an over-approximation of the behavior of the program by analyzing the whole program. And that whole program contains your application code and all the library dependencies that your application code depend on. And this is what we call a whole program. So you get the whole program, do the analysis, get an over-approximation of the result. However, sometimes if this whole program is not available, maybe you don't have all the library dependencies, maybe the library dependencies are just too big to analyze and you don't have enough resources for them, so you might want to resort to some other solutions. One possible solution is to say, well, I'm not going to analyze anything other than my single function or my single file or my single package or the work item that I'm working on as a developer. I just don't care about the outside world. I'm just going to assume it can do whatever it wants with my code, and I'm going to be conservative about it. But this would yield a highly imprecise call graph. This would be a very imprecise call graph because what that assumption says is, well, if this code can do anything to your program, well, it can create any object, can modify any field, can call any method, so the interactions are quickly going to generate a lot of false positives for the call graph. And this would just increase the imprecision of the call graph. On the other extreme, you can also assume, well, yes, I don't have access to those methods. Yes, I don't know how to over-approximate it, to have any assumptions about them. So instead of making any assumptions about them, I'm just going to pretend that they do not exist. That piece of code does not exist. Anything outside my point of interest does not exist. Obviously, this is going to yield an unsound solution or an incomplete solution because you are going to miss potential opportunities for a potential behavior of the program at runtime that is not modeled by having this incomplete call graph or unsound call graph. So to work around all these conservative algorithms, unsound algorithms, incomplete solutions, we are going to discuss in our lecture in the next couple of minutes, and most probably continue for the vast majority of it on Tuesday, with various call graph algorithms that have an increasing level of precision that we're going to talk about, and all are drawn from they are all implemented in various different analysis frameworks, but I'm going to talk specifically about their implementation, about their ideas in general, but specifically about their implementation in the SUT analysis framework. And I'm also going to give you, most probably on Thursday, but if we don't have time for it on Thursday, I'm going to do it, on Tuesday. But if we don't have time for it on Tuesday, I'm probably going to do it on Thursday next week. A hands-on experience by just getting a piece of code or a bunch of programs, running all these analysis frameworks, all these analysis algorithms, call graph analyses, on them using SUT, and showing you how the precision of each analysis algorithm would actually pan out in practice. And I'm also going to make those hands-on programs and the analyses and the code and everything related to it available to you on eClass, so you can just look it up on the link that I'm going to have available on eClass, so you can check it out and try it out on your own as well. Those algorithms, as I said, they're going to be an increasing level of precision. We're going to talk about class hierarchy analysis, rapid type analysis, variable type analysis, and then propagation-based analysis called Spark that was also part of the SUT framework. I'm actually going to stop here for today, and I'm going to pause for a couple of minutes just in case you have any questions about what we have discussed today, whether it's lattice theory, whether it's monotone framework, Tarski's theorem, Kleen's theorem, call graphs, anything that we have discussed so far in today's lecture or in the course so far. I'm happy to answer any questions about them in the remaining minute or two. Sure. Sure. Mm-hmm. Mm-hmm. Right. Okay. So this is, maybe I'll just show it like that. So this is the slide that tells you the conditions of determining whether a hash diagram is a lattice or not, right? If you notice, if it is going to be a lattice if for all pairs of elements x and y. I'm not talking about all possible subsets of U. I'm just talking, pick any two pairs. If you can find a least upper bound for these two pairs and the greatest lower bound for these two pairs, then it is going to be a lattice. Does that make sense? Okay, so a complete lattice is actually a more generalized way of saying this. or a generalization over this assumption. So a complete lattice adds the condition that not just for any two pairs, it could be for any possible subset. So that subset can have two elements in it, can have three elements, can have four elements, can have five elements, can have all the elements. You need to be able to get to find a least upper bound or a join and a greatest lower bound or a meet for that subset that is not necessarily one of these elements of that subset. It could be an element as long as it's an element from the universe or from the set itself. So in that sense, I mean, it depends on your definition of more strict, but I would say the complete lattice is a further restriction because it should apply to all possible subsets of your lattice, not just every pair of elements in the lattice. Does that answer your question? Okay, sounds good. Yes, exactly. And just like Giaki was saying now on the Zoom chat, a complete lattice is eventually a lattice after all, but a lattice may not be complete. So think about it. Come up with examples where you have a lattice that is not complete, and have a counter example for it. And let's have a discussion in next lecture, or over the E-class forum as well. Non-complete is a special case where subset has size of 2. I don't think I get your question, Mohaimin. What do you mean by that? Right. So a regular lattice would just be. I wouldn't put it this way just to avoid any confusion. I would just put it the other way, that a complete lattice is a generalization of the special case, which is a lattice that has that property true for every pair of elements. So the subset is of size 2. But if you can find that join and meet, or greatest lower bound and least upper bound for all possible subsets, then it's going to be a complete lattice. All right, sounds good. Well, we are over the official class time, everyone. So I think this would be a good time to perhaps end the lecture. If you have any questions about anything that we have discussed so far, please reach out to Ifaz or myself. Post on the E-class forum. We'll be happy to help you out. And I hope you're going to have a nice weekend, and I'll see you on Tuesday next week. Thank you, everyone.